It's a pleasure. And
well, we didn't do the customary announcement. It's great to have Spenta here. They're giving us a chemistry talk. And Spenta really does not need any production, so that makes my life very easy. And we will have some
Okay.
dinner with Spenta by arrangement with people.
Yeah, we'll check with Spenta and Sandeep.
Okay, fine. Thank you. Okay, so I am going to talk about some work which we have been doing over the last year with Gautam Mandal and Pranjal Nayak. And I'd like to thank the Infosys Foundation for more than one reason over here, and for supporting the idea of the usefulness of useless knowledge.
And also this particular sense.
Yes. More than one, I said. And I also heard some very sad news this morning, actually. So Professor N. Kumar, who is a very good friend of mine, sort of a mentor and advisor in many ways. He was the director of the Raman Research Institute for many years. He passed away this morning, so I'd like to dedicate this seminar to his memory. All right, so let's get back to physics now. So I'll begin with a bit of history. The search for soluble models to resolve, I won't be looking at you because I have to be very careful what you see there, right? So the search for soluble models to resolve problems concerning unitarity and information loss have a very long history, actually, beginning approximately even earlier than the 1990s. And one of the models that was very popular in those days was a non-perturbative definition of two-dimensional string theory, which was called the C = 1 matrix model. Now, if you are not familiar with all this, which given your age you may not be, you can have a look at the slides later and try to navigate the history if you are interested. So this is a model of, it's a quantum mechanics again of Hermitian matrices. The potentials are tuned in such a way so that you have a continuum string theory in 2 dimensions. And the model maps into an exactly soluble problem of many fermions. And these fermions have around the Fermi C massless excitations. And these massless excitations get identified with massless scalar in 2-dimensional string theory. And today you will recognize this as something what is called the boundary to bulk map, that a field in the matrix model can be mapped by a very nonlinear transformation into a field in the string theory, and it satisfies this type of equation, which really comes from the dilettante gravity Lagrangian of 2-dimensional string theory. So if you look for the beta function solutions of 2-dimensional string theory, this is the sort of leading order action you'll arrive at. Okay, now the fact that there was a matrix model that mapped into 2-dimensional string theory via the Liouville mode connection encouraged us to look for some more interesting solutions actually in this problem. It was believed that 2-dimensional string theory doesn't have any more interesting solutions, but somehow with Gautam Mandal and Anirvan Sengupta, we found a black hole solution in this model, and it's a perfectly legitimate black hole solution, and which was also co-discovered by Ed Witten and a little bit earlier by Elitzur, Forgier, and Rabinovici in the form of the conformal field theory, which Witten had actually proposed it as. Okay, so there was a matrix model and there was a black hole. So that's great news, because then then you can solve the model at finite n and learn how to take the large n limit, and hopefully solve some of the important questions of black hole physics. However, there is no signature of the black hole in the singlet sector of the C equal to 1 matrix model. The singlet sector means a sector in which all operators of these matrix model are UN invariant actually. So they are just the eigenvalues, okay, or functions of the eigenvalues. And however way you try to deform this model, there is no way in which you can produce anything close to an object that thermalizes in the two-dimensional string theory. And you know, I mean, you know this at the back of the mind, yet you want to not sort of admit it, but for many years. The reason is very simple. This model has infinite number of conserved charges, period. If you have infinite number of conserved charges, there is no chance of describing an object like a black hole in the bulk. But
in this situation, is there some analog quasi-normal modes in the bulk?
Nobody did that calculation. At least I'm not aware actually. Yeah, I don't know that. However, I sort of never give up, you know. So while preparing this talk and having some discussions in Bangalore, you can play the trick which at that time we didn't know how to play actually. So you look for matrix models, but at finite temperature. If you have finite temperature, then you need to have a holonomy in the boundary conditions, and then you get depending on the type of Lagrangian of the matrix model, you get a god-awful effective action of the unitary matrix. This is calculable, and I have a feeling that if one does this calculation, one will pick up potentials which can sort of have all the valleys and maxima which we have studied in higher dimensional models, especially Shiraz.
You're aware of the KKK paper?
Yes, I'm aware of the KKK paper, but the KKK paper is nothing but putting the C equal to 1 matrix model at finite temperature, but they don't have an effective action of the holonomy. You see, they make a connection with integrable systems, and I can discuss that later, but they do not have an effective action. KKK is Kutasov, Kazakov, Kostov. Yep.
They introduce chemical potentials for vortices.
But I don't see an effective potential. All right. You have a comment?
My understanding was that in order to get the black hole, they needed to do a non-normalizable derivation of the finite temperature system. You're searching for the black hole as a solution, a normalizable solution. And there was this business about the winding mode being
Yes. So the winding mode is there. That's the U mode, right?
Maybe later.
Yeah, sure. Okay, so then many years go by, and black holes are interesting, and we come to ADS-CFT. And then there is a very important development, and this important development has to do with the fact that there is a new diagnostic of black hole properties. That's the key point. And this was discovered by Kitaev and by Schenker, Stanford, Maldacena, and the Susskind group. They proposed a new diagnostic of black hole properties, and that has to do with the fact that black holes are the most efficient scramblers of information, and they will saturate the so-called quantum Lyapunov exponent. So this is a very important development, I think, and many times people write with h bar equal to 1, so I've just put h bar here to make sure that this is a very highly quantum, very non-perturbative answer. And Kitaev proposed a slightly modified version of the Sachdev-Ye-Kitaev model, which is soluble at large n, and which saturates this bound. So let me just flash something which you are all familiar with. I am not bothered very much about random couplings. I'll tell you why later on. Each coupling defines one unitary Hamiltonian, and if you sample this type of space, at least in the large n limit, the quenching and the annealed properties for this random coupling give the same answer. So here is the model, and which you all know, and it has the following important properties. Firstly, it's well defined at finite end. This is actually the most important point. This large end limit on which we have spent years actually is the problem. As we'll discuss at the end. But the important point is it is really soluble at large n and strong coupling. Okay, so that's the first important thing. And secondly, that there is an emergent symmetry in strong coupling limit. That's, I think, somehow at the back of this ability to do these calculations. And thirdly, if you compute the appropriate 4-point function in real time, then you get this growing exponential in time. So you take log on both sides, and this is the ramp that people talk about actually. And very importantly, it is the coefficient over here is beta j upon capital N, where N is the number of degrees of freedom, and that gives rise to a new time scale in this problem, which people call the scrambling time. The fourth point, which is important in this model, it has a very well-defined thermodynamics. It's a well-defined canonical partition function, and I think this is rather important. And so people have computed the free energy, and it has a very important point that the free energy is proportional to the temperature over here. If you look at the density of states coming from this type of partition function, then it has a typical square root of energy type of behavior, which is very reminiscent of the spectra of random matrices. So these are the important features of the SYK model, and I believe that the models of Witten and Kurov and Klebanov and others and their students also reproduce at large n the same results. Okay, now I'll just give you a very lightning review of the SYK model. I don't know whether it is a necessary thing, Shiraz or Gautam.
I think
it's okay. All right. So, as I said, it's a Hamiltonian with a random coupling. So you average over these random couplings, which are Gaussian. It is possible to do that very easily. And you write down the so-called Schwinger-Dyson equations, which you usually would do. And the Schwinger-Dyson equations turn out to be written in terms of two bilocal fields. Okay. So my office. Oh, I'm sorry. So there are these two bilocal fields. I will not detail it. G of tau 1, tau 2 is the expectation value of the 2-point function in an arbitrary state, and this is some conjugate coupling. And if you write down the Schwinger-Dyson equations, they take the following form, where omega is a frequency. If you're on the circle with a finite temperature, this is quantized, otherwise it's a continuum. And these equations can be derived from a classical action. Okay. Now all this is sort of, this type of technology is very well known in other in solving other problems in the large n limit, but it's very nice that it appears here. And these equations can be derived from this action, and in fact you can argue that the partition function in the large n limit is given by this bilocal integral over bilocal fields with this particular action. Okay. So this is the formalism. Okay. So now you have the equations. Now the task is how to solve them, and that turns out to be an extremely difficult problem. It's horrible. Okay, but now what Kitaev realized is that if you look at the deep infrared, means if you look at frequencies, typical frequencies which are much less than the value of the coupling J, which is dimensional in the Lagrangian I had written down, or if you look at beta J much greater than 1, this is what you would call the strong coupling end. This is also the infrared end. Then this action has a surprising emergent symmetry. I think this symmetry was actually known to Sachdev and collaborators in the past, which has a exact symmetry, this action. Basically what you do is that if you if you drop the d by d tau term from here, from this Pfaffian, then this is clear, all right. Where f is any function, which is called, f is any function, is an element of this diffeomorphism group in one dimension. I have chosen this notation 1 to mean R1 if you are working with non-compact Euclidean time. By the way, I am in Euclidean time all the time here. And 1 also represents S1 if you are at finite temperature. So you have this this type of symmetry, and that determines uniquely the exponents of this Green's function. Okay, over here. All right. And at finite temperature, if you want to find out this answer, you just make this type of transformation from the line to the circle, and these are the well-known answers. The important point over here is that this answer breaks the symmetry of diff1 to SL2R. Okay, that's the important thing. So you have a classical theory or a quantum theory which is invariant under a certain large symmetry, but the classical solution breaks the symmetry. So you say diff1 is spontaneously broken to SL2R, and by SL2R here I mean just these simple transformations where A, B, C, D are just real numbers. Okay, this forms a group. It's a very well-known group. Okay, so we have a huge symmetry in the infrared which is broken by the classical solutions in the infrared. And that's very nice. This is all familiar physics now, because if you want to study the low-lying modes, the low-lying spectrum of this theory, you simply look at this coset diff1 upon SL2R. This is the way we study pion physics, for example, in high energy physics, or even in condensed matter physics. So these are some pictures over here. So by 1, as I said, I'll mean R1 and S1. And so the important thing is that you take the classical solution and consider the orbit of the classical solution. By orbit, I mean basically take the solution and apply the transformation. So it generates an orbit. And as we saw, when beta j goes to infinity in the deep infrared at strong coupling, this action has this symmetry that is invariant under this. So the action is the same all along the orbit. Okay? If the action is the same all along the orbit, then the integral on this orbit is obviously divergent, because this measure is divergent, it's infinite. Okay? So this is a very simple reason why there is big trouble if you worked with this orbit. So then Kitaev and then of course Maldacena, Stanford worked out all those things in great detail. Turned to the hard problem of how to solve this Schwinger-Dyson equation, not for beta j equal to infinity, but for finite but large beta j. And then this is a hard problem, really. They found a solution, and this solution is a series in 1 upon j tau, and at finite temperature it's a series in 1 upon beta j. So you can correct for the solution. But you see immediately something which had a very well-defined scaling law under a certain symmetry just gets violated, actually, because of this additional term. So even your SL2R symmetry is now explicitly broken. That's great, because if the SL2R symmetry is explicitly broken, you have a new orbit now. So this is the conformally invariant solution, or the scaling solution, which is corrected. This is the orbit. So you have a corrected orbit now. So perturbation theory around this orbit is perfectly well defined, and one can calculate the effective action of the low-lying spectrum of this theory. Now let me just make a point to you that what is the deep point here? The deep point here is that it is the low-lying spectrum of this theory in the large n limit that is responsible for the fact that the model is maximally chaotic. So this is the thing we have to really study and worry about in the future. I have not ever thought about it this way before, but it's the low-lying spectrum that is, and in a large n limit, this spectrum becomes a continuum and leads to hydrodynamics and this chaotic type of behaviors. I'm not saying everything very precisely because it will take me a long time to say things very precisely, but you understand what I'm saying. Okay.
This is the
Yes.
spectrum of the Euclidean problem.
Yes.
It's not the spectrum of states.
This is the spectrum of the dimensions, or the Hamiltonian of the SYK model.
I didn't understand.
See, so let me say the details. So what you do is that you have this orbit now. Of classical solution, you will make a small oscillations expansion around it, a small perturbation, right? And you will diagonalize that perturbation. So that perturbation is diagonalized by a set of eigenvectors and eigenvalues actually. So it is these eigenvalues I am referring to over here. And it is these eigenvalues which are sort of, there is a bunching, large number of eigenvalues which are low-lying. They are not degenerate. And then there is a spectrum which is equally spaced and goes up to infinity and corresponds to this. Yes.
Are there states in the theory corresponding to these diffeomorphisms?
States in the theory correspond? I would think so, yes. My answer is yes. Because you see, we are working with a quantum mechanics problem, right, of a Hamiltonian, right? And we are looking at the spectrum of this Hamiltonian, right? And the spectrum I'm saying is organized as follows. You have this large number of levels near the zero of energy, and then there is a discrete gap spectrum.
But if sorry to interrupt.
Sure, sure.
But suppose we compute the partition function. Maybe you're doing some other calculation. Suppose we compute the partition function.
Yes.
Then there's the saddle point value of the partition function, and all that this stuff is doing is calculating the first 1/n corrections around the.
But that's what I'm saying. These are order 1 if you scale out the coupling.
Order 1 corrections to an order n.
Yes, yes, yes.
So why am I associating these order 1 corrections by themselves with states? Looks like just correcting the saddle point, which itself is order n.
I understand what you're asking. What you're asking is that usually if you have a solution and you do perturbation theory around it, that spectrum of states, that is the spectrum of the Hamiltonian around a classical solution.
But
and it's order 1 usually.
But now the classical solution itself corresponds to lots of states.
Yes, exactly. So that's the point actually. So that this, very good. So these more massive modes that I talked about just now can be all calculated around this green orbit. There is no need to do all this complicated stuff. And that spectrum is organized according to SL2R symmetry, right? You don't have to do all this complicated new classical solution in order to compute the spectrum which I was mentioning over here. But it is this orbit which actually I am quantizing. I'm quantizing it. Yeah, sure. Maybe the words you don't understand, or the...
No, just associating the spectrum of this quantization with states in the Hamiltonian.
Yes, okay.
If the solution was let's say a soliton, you were doing that I would understand. But here the solution itself is a large number of states. So it looks to me that what these fluctuations.
So Shiraz, as you say soliton, so let's take soliton quantization. So we introduce collective coordinates, right? Look at the orbit of the soliton under the appropriate symmetry group, right? And then we compute the action of the theory on this orbit, and that is of order 1 upon h bar, just the same order as the classical solution.
And that's perfectly fine.
Yes.
But it's one big difference here is that in the soliton we've got time independent configurations, and then you make them slowly time varying.
Yes.
And then you compute the action of this.
Right.
Here your diffeomorphisms are in time.
Yes.
So there wasn't like a set of time independent configurations of the action to start. There wasn't a manifold of time independent solutions.
See, okay, let me put it this way, that okay, you arrive at this Schwarzian, okay, which tells you about the effective theory of these pions in some sense of the reparametrization group. And you compute the partition function, and then you look at the density of states, which I mentioned. So that goes as exponential of square root of E or something, right?
Yes.
Now, that should tell you that something about the spectrum of this Hamiltonian, right?
Yeah, but it's a finite temperature is very subleading spectrum, because mainly the spectrum is contained in the saddle point.
This is not subleading because because the Schwarzian goes as n upon beta j. Why you are saying it's subleading?
Subleading because it's just one mode. You compute a determinant of one mode, you will get something
But
independent.
this
the
is
action has an n over beta j, but when you
right.
compute the determinant, it won't have any. Right? Because you absorb away the. When you come e to the power alpha x squared, the determinant of that is independent of alpha.
Actually, I'm not understanding your question. I am saying that this SYK model Hamiltonian has a spectrum. Every Hamiltonian has a spectrum.
It has a spectrum.
Right.
I'm
It
just asking whether the diffeomorphisms there's a sense in which you can identify the contribution of the diffeomorphisms to a particular part of the spectrum. The full spectrum is some huge spectrum, right? So got order n states.
Yes.
What you get from the Schwarzian is order 1. Because it's just one mode.
This
If you
I'm,
quantize
this is exactly what I'm not sure of, because my picture is a little different. That there is a whole band of low-lying states.
Whole band, but it's like one field theory. Field theory in time, one mode in time. It's like x of t, right? Like a harmonic oscillator x of t.
But there are lots of them.
Why? It's just x of t.
No, but the x of t is in just the one-dimensional system.
Uh-huh.
But in here, there are lots of them, right?
Why? I thought it was epsilon of t. The diffeomorphism is a function of time.
Yes, but
I'm probably misunderstanding. I'm sorry. I thought it had as many degrees of freedom roughly as a harmonic oscillator. To the extent that you think of it as degrees of freedom. Whereas the system has many modes, got like n degrees of freedom. This is some small perturbation.
this is not a small perturbation on this orbit. I'm computing the action on this orbit, right?
Yeah, there are some correlation functions that receive very important contributions from this.
Yes.
This I told you.
Right.
You compute a 4-point function
Right.
out of time order, and it receives its leading contribution of this. This I
Right.
told you. But I just want to understand whether you are associating some part of the spectrum in some clear way with this.
Yes, so that was my understanding actually. It's very much like associating a pion spectrum in theories of spontaneous chiral symmetry breaking.
I think there's a bit of difference here because if you consider the Euclidean time lattice,
Yes.
then that has all these solutions. But the point is, eventually, all these epsilon of t fellows, okay, they are like there is no further time.
I understand.
In which these guys are evolving. So if you consider Euclidean lattice stat mech, then this epsilon of t are all different solutions. But if you want to go back to the original zero dimensional quantum mechanics, okay, then it's just one degree of freedom of t, meaning that the various functions of t are just the various Fourier modes.
So your question is that if I actually look at the solution of the problem as a Hamiltonian problem, then I look at the wave functions. I would imagine that these wave functions are parametrized by this diffeomorphism. But I think that I understand the problem. There is a problem, as Gautam said, that you are sitting at a fixed time basically.
Exactly.
And yes,
Basically,
diffeomorphism
all
of
of
what?
these guys are like zero modes. There is no further. That is the reason why there is no pion kinetic energy in this.
Yes, yes.
The Schwarzian is actually a pion mass. You have to break it.
So
Otherwise
what would you say is the reflection of this symmetry in the Hamiltonian framework? That's the question that you are asking, right?
Yeah.
What is it?
Yeah, I don't know.
I don't know the answer. Yeah, okay.
This question is, the answer is not clear.
Yes. Okay.
I think it's a little bit like holonomics. It seems to me like a purely Euclidean thing. When you do a path integral of gauge theories, you do an integral of a holonomy.
Yes.
It has a very deep impact on the Lorentzian answer,
Yes.
but there's no holonomy in the Lorentzian picture. It
Yes.
comes from a different place. It comes from Gaussian.
That's right.
I think something like that. But I don't
Something like that. Yeah, okay, I agree. Thanks. Yeah, okay,
You are
good.
saying this just by way of analogy?
know.
or,
Just
Yeah, because this calculation I am doing is totally in Euclidean space. But those people have also done the calculation in Lorentzian signature, but okay, now what?
Counting-wise, I see your point. It's the one function.
one function. But if I was to take my point to the
Where
extreme,
is-
I would say that
where is the
even
plug?
one function is not by itself visible in the Lorentzian problem at all. because the Lorentzian problem doesn't have a, I mean, if you solve Hamiltonian, there's no time for which you can do a diffeomorphism.
Okay, I'll continue.
Yeah.
All right. So then this is the famous effective action, which is the Schwarzian, and there is a number over here which depends upon the. This number is dictated by the ultraviolet properties of the model, but this is some sort of a universal answer actually for any model which has this type of dynamics of emergent symmetries which are broken to SL2R, which is also explicitly broken. So this action is invariant under SL2R though. So in a sense, okay, fine. Now, if you have this action, you can compute a propagator over here, Euclidean propagator, and then do this calculation again, exchange of this mode, and that gives rise to the chaos bound over here. Now this is not a Euclidean calculation, or it's a calculation in you know, analytic continuation appropriately, but I will not detail that, and you get this answer. So similar conclusions can be drawn for the tensor models.
And that exponential, that
yes.
Basically the exponential is simply the fact that the Schwarzian action itself has an exponential solution.
Yes.
That's essentially right?
But those exponential solutions actually can be, you see, okay, not really. There is a comment on that by these people, that that particular solution can be gauged away by SL2R. So this is the no. So no.
But there is a solution with the same coefficient, right?
Same coefficient? No.
I mean,
There's
the propagator is 1 over, you know.
Classical solution will not have those coefficients because I mean, this guy is just sitting outside.
No, but the 2 pi by beta is there.
Yes. Right. But that solution actually can be gauged away, according to these people.
Okay,
these people mean Malsena and company.
But in the end, it will be coming from the exchange of this.
Exactly. That is a physically important thing.
And the exchange knows about the classical solutions of those.
Yes.
So
the exchange.
However you say it, in the end, I think the fact that this thing has that as the classical solution is the key algebraic point, right? Whether it's conceptual. You know, at least algebraically, you've got something's hitting this mode. It is growing, and then it's hitting something else. And its growth is causing that. Now, what conceptual, I don't know how to say. I mean, it seems to me, if you just look at the calculations, that's basically it.
Yeah. So I mean, so you agree that it is this propagator actually is very important.
Exactly.
And this propagator has beta j upon m precisely because of the thing outside over here. And these two additions of the propagator are basically removed by SL2R gauge transformations. This is it. So this is the hydrodynamic type of mode which is exchanged between these particles, and that leads to this type of answer. It's a great result. Okay, all right, so this is a review of the SYK model. You have any questions or any clarifications? All right, so now let me start the second part of my talk actually. So of course one of the other the fruits of the ADS-CFT correspondence which hangs very high is how to prove the correspondence. It's a conjecture, right? I mean, with lots and lots of evidence, very solid evidence. But starting from the boundary theory, it is very hard to imagine how to derive the bulk dual, right? So we saw here an opportunity to do that in a very simple situation. So maybe it's not a proof really, but it definitely motivates. So let me just talk about this a little bit now. So, so the SYK model, as we noted, has an emergent diff1 symmetry, and which is broken to SL2R. So the low-lying states let me just put them in parenthesis, low-lying states, which are described by the Schwarzian, lie on this orbit. Okay. Hence, one can consider the quantization of the coadjoint orbit of diff1 mod SL2R. Now, why is that such a good motivation? All right, so let me just very briefly tell you what is this business of the coadjoint orbits all about, in a very simple example. So if you want to, for example, do the quantum mechanics of a spin in a magnetic field, then you have, the algebra of spin operators, right? And then the next question you ask is, how do I write a path integral to quantize this type of problem, right? So the way you write the path integral is there are various ways of doing it. That you talk about the classical spin, which is the you will say expectation value in some coherent space of this coherent state of this model. So you define some sort of a classical spin which is normalized appropriately, and that object basically lives on a sphere of various radii, right? And those radii are given by the representation of the SL2R, of the SU2 group you are in. So you essentially arrive at doing a path integral on a sphere. Now this sphere turns out to be your so-called coadjoint orbit. It is a even dimensional manifold. It has a symplectic form, which is nothing here but just the area element of the sphere. And you're very happy, and this is what it is. So now I want to do this for any compact Lie group. This is exactly the way it works. But for a Virasoro or for Kac-Moody or these infinite dimensional algebras, this is a very hard problem. Of course, hard problems have been worked on by people many decades ago. So there are many Russian papers on this, but there is, as usual, a fantastic review by Edwitton that explains everybody's all works. It's called the coadjoint orbits of the Virasoro group or something. That's the name of the paper, and most of our knowledge we have got from there. So for Virasoro and for Kac-Moody, the quantization of these coadjoint orbits naturally produces, in the case of the Kac-Moody algebra, the Wess-Zumino-Witten model. The full model basically is essentially an action on the coadjoint orbit of this infinite dimensional algebra. And similarly for Virasoro, the coadjoint orbit turns out to be a theory of two-dimensional quantum gravity. I can explain this to you, but this is a very long story, so I don't want to there's a long way to go for me over here.
Just to understand this.
Yes,
in
yes.
the case of SU2,
yes.
when you quantize different coadjoint orbits,
yes.
you get different representations.
Exactly.
Now, is the same thing true here?
Yes, I mean, I will come to that actually. So the first thing you have to worry about in the SYK model, and it's a result which nobody has proved, or is the fact that we have this Virasoro type of algebra, but nobody computed the central charge of this object. I mean, what is the central charge of this symmetry group of the SYK model? That has not been calculated. I would imagine that there is a central extension, and the central charge should reflect the number of degrees of freedom, but it has not been computed. But I'll assume for this talk that such a central extension exists. In fact, from the mathematician's point of view, you can always take a central extension of these type of algebras, and there's a lot of fancy words associated with it, which I will not use. But let me assume that there is a central extension of diff1, and our proposal is that the dual representation of the SYK model and related models emerges from a quantization of the coadjoint orbit of this coset. This coset, because SL2R is, I am using some physics, that SL2R is an important symmetry of the SYK model. So So a lot of people have worked on this, and the important papers in this direction are due to Alexeyev and Saakashvili and Balram Rai and Rogers many years ago, showed that if you look at the coadjoint orbit of this coset, then you can describe it in terms of a set of curves in a set of reparameterizations labeled by sigma. Okay, you could have put the sigma label over here. So you see how a two-dimensional object is getting generated on the coadjoint orbit. And they found the action. They calculated the action, and they found it to be given by this formula in terms of this field f of tau sigma. Okay. And now if you have SL2R as this coset over here, then something more interesting happens, that this B naught over here gets fixed. The orbit is fixed by this numbers, where C is the central charge and N is arbitrary integer.
If you quantize this epsilon, then you get the representation of diff by SL2R.
Yes, this is the point. This is the whole point of this development of mathematics, in which group representation theory is reduced to a quantum mechanics problem on the coadjoint orbit of that group. Yeah. So I recommend you to read Witten's paper. Actually, it's very beautifully written as usual, and he explains this whole scenario, but he doesn't do the calculation that I mentioned over here. This calculation was done by Alexeyev, Saakashvili, and Rai and Rogers.
So does that mean it reproduces, it gives you the vacuum module of the chiral Virasoro algebra? Because by SL2R means the vacuum module, right?
Yes, yes, yes.
Quantization of this
Right.
is the vacuum.
Right, right.
Vacuum character.
That's right. That's right. Yeah. So the other way of putting it is that if you have a group, you have a bracket in a group, right? You have a idea of a Poisson bracket or a commutator. So this method, what it does is that it imprints this commutator idea onto the coadjoint orbit, and that becomes a symplectic form. And once you have a symplectic form, you can do the action. And this is also explained in this more recent paper by Witten and Douglas Stanford. Many of these things are talked about there also. But anyway, this is a very old result, and this result we knew from many years.
But just to understand that clearly,
Yes.
the diff part is just like one half of the Virasoro solution, right? It's just, if I think of tau as Z, it's
Yeah.
just one half of the Virasoro solution. So that's something familiar to.
Yeah, it's basically basically it's the maps from a circle.
So that anything that would implement the Virasoro algebra would be a quantization of diff.
Yes.
I'm trying to understand what diff by SL2R means. Those representations that are SL2R, that are built out of an SL2R invariant vacuum. And
Yes.
therefore the identity.
That's right. So these representations are basically labeled by this number over here, B naught. So Shiraz, one thing is very important, that there are lots of subgroups actually that you can talk about. But the situation is totally unclear beyond U1 and S1 and SL2R. I mean, if you quotient by some other subgroup, the quantization is not known.
I see.
Yeah.
I see. What was B naught again?
Yeah, B naught is a parameter actually that appears over here. And for example, in the spin model, for example, I mean, you could say that B naught is something that, yeah, it specifies the orbit.
Of flux.
Yes, yes,
I see. So different values of B naught give you different characters.
Yeah.
yes.
Now this I'm getting confused about, because I thought there was one unique SL2R invariant.
So this is with the vacuum model, Riemann applies for B naught equilibrium.
And then what are the other ones?
We don't know. Important question. So let me just come to that.
Okay.
So what we know, and this is an interesting thing to do, is that if you set B naught to 0,
Right.
okay, then this part of the action over here, which reflects the symplectic form, exactly maps into this action written down by Polyakov, in which the metric is just d sigma of f. So this is a math identity, and it's great that something like this actually leads to some 2D gravity. Amazing. Of course, but this is not our full story, because we know physically that we have to look for a solution of this theory, which is ADS2, right? I mean, we know that from SYK model intuition that you will look for some solution which is ADS2 of these equations. And for that, of course, then now, I don't want to go into a lot of detail, but a lot of trial and error brought us to this. Oh God, can you see the whole thing? Yeah, you can. All right, so this is the first term. Then we added a cosmological constant term. Why? Because we want ADS2. And we introduced boundary terms over here, okay, because this is a theory in a given region of two-dimensional space-time. But that actually introduces a lot of subtleties with which we'll be occupied for the rest of the talk. So this is the bulk part of the action, and these are the boundary terms which are sort of needed if the equations of motion are a solution of a variation problem. All right. So cosmological constant is there, then this b square is a parameter over here which is related to the central charge. Then gamma is the induced metric on the boundary. This is the external extrinsic curvature. And you may wonder actually, and many people have asked this question, that why didn't you add r times 1 upon box to the power 2 or 3 or 4, because they are all allowed, no? I mean, people ask these questions naturally, because they are allowed. B square is dimensionless here. So we looked at the classical solutions of those types of models actually, and it's interesting that they do not admit asymptotic ADS2 geometries. So in some sense, that's a fixation of our theory actually by these physical requirements.
So
yes.
Second boundary term.
Yeah.
Two boundary terms, right?
Yes.
This box is in box of bulk or the boundary?
No, no, no.
Right.
That's bulk.
And the third one?
It's you see, so box inverse is a Green's function, no? So this Green's function is in the bulk. Now that Green's function has to be evaluated at the boundary, right? Like we do in electrodynamics.
Yeah, but kappa is a quantity on the boundary.
Yes.
But that box has to be a box of the boundary.
View the boundary as a submanifold object.
Yeah.
Okay.
So it's like a charge density.
Both legs of the bulk Green's function and
Yes.
boundary.
And this Green's function is very appropriately defined so that it vanishes in a certain way at the boundary, without which many of the calculations will not work. And this is all math kosher. I mean, okay. All right. So now we derive the equations of motion, which are quite difficult. I have written them in this very simple-looking form, but this chi over here is essentially an integral transform of the scalar curvature. So you have these equations of motion of this model, and now clearly we have to learn how to solve these equations. So now starts our real job, how to solve this problem. It's a very difficult problem, really. So we will present the simplest smooth solutions over here in this talk.
Euclidean or Lorentzian space?
I am always Euclidean, Shiraz, because Lorentzian is another. The boundaries are different, and there are two boundaries, and it's complicated. I mean, it's maybe the real stuff, but. So we look for solutions of this form. Okay. And here G hat essentially is the ADS2 metric. So firstly, you convince yourself that ADS2 is actually a solution of these equations. You can do that. And then we'll.
You're looking for solutions with what boundary conditions, please? Or you'll tell us?
Sorry.
You're looking for solutions with some boundary conditions?
Yes. The boundary is this one.
I see. So the boundary conditions
Is we are looking for the solution for the conformal part of the metric in the background of ADS2.
No, but at the back, is there some boundary condition?
I'll
at
come
the
to
boundary
that.
of ADS?
I'll come to that actually. I'll come to that. Yeah. Okay. So this is the first part. So you solve these equations. So then you look at the first equation and you substitute this ansatz, and you come up with a exact solution of this problem in terms of a holomorphic function g of z. And you then calculate this metric in terms of this new solution, and this defines a new class of metrics. Now you'll wonder, why are these different metrics? And the reason why you can say these are different metrics, because there's a very, very, very beautiful theorem which says that if you look at metrics like this, then the distance calculated in this space using the metric with g is always less than, exactly less than the distance calculated in ADS2, and equal if this function is an element of the isometry of ADS2, which is SL2R. This is a very famous theorem, Schwarzian theorem. You must all be knowing about this, because this was used by Maldacena, Schenker, and Stanford to prove the chaos bound. This theorem was used there, so it's not something totally unknown to our community. Okay, so you get a new class of metrics. All right, fine, but then you have to satisfy these two sort of additional constraint type equations. Okay, and you do that, and what you find is that the solution for g of z is given by basically this type of a function, az plus b, cz plus d, where a, b, c, d are all complex numbers now. Okay, so there are 6 independent numbers. All right. So 3 of those numbers actually really correspond to SL2R, which leaves the boundary of our space. Remember, our space was the right half plane, which is defined by z plus z bar equal to 0. Shiraz, something's bothering you?
Yeah, sorry, could you go back to your Lagrangian?
Sure. Yeah.
So your Lagrangian had only R, and then at some point you introduced a phi, right? Is that?
Yes, but that is to do the solutions actually.
I
I mean,
that's just look for phi.
Yeah, the equations are this monstrosity actually here. Okay, so
That's the one. Step 1, so go down below, go a little below the step 1 key. Yeah,
It's
so
here.
That's
See.
This parameter is
Here. So I'm looking for solutions like that actually.
And I think, can you integrate out the 1 by del squared by introducing the?
Yes, so this
Phi was that.
yeah. So this so this chi which I have over here, which is given essentially as 1 upon box r. You can think of writing your theory as a local theory in terms of these chi variables also. You can do that. Not a problem. It somehow looks like some dilettante type of thing, but I want to stick to this for a certain reason.
And just to get a sense,
Sure.
in terms of phi, reaction is how many derivatives? I mean, if you plug in this equation, you look at the equation of motion for phi.
Second derivative equations.
There's 2 derivatives.
2 derivatives, yes. So explicitly you can see that if you do this also in this ansatz, you essentially get a second order equation, and now the constraint equations are also second order. Okay, and then you solve these constraint equations, and the solution for g of z is nothing but this fractional linear transformation in the complex plane. And I'm saying that parts of this solution are isometries of SL2, of ADS2, which is not important for me. It's the other part.
So you get it essentially unique, meaning 4
Yeah.
parameter set of solutions, even without putting one.
Yeah.
Okay.
Now, so what I'm interested therefore is those functions z of z which are not part of SL2R and which do change the boundary. So there's a 3 parameter deformation that changes the boundary, but I want to consider for this our purposes just a simple 1 parameter deformation. And if you do that, then you can solve for this. We know the classical solution, right, over here for phi. We know the classical solution. You can plug it all in, and finally the answer turns out to be something like this, which you have 1 parameter here, which I would like to now say that is small, because in this subject now we have to introduce a cutoff in the theory of gravity. Now,
I
yeah,
you had
yeah.
a 3 parameter solution. how does that become a one parameter?
Yeah, by my I mean, I'm looking at the simplest part actually.
Okay.
Yeah, just a one parameter deformation.
Okay.
I don't know exactly what the action would be, but it's interesting to think about that also. So first let me say that in this problem I'm introducing a certain cutoff. Okay, by cutoff I mean the usual thing that my space ends distance delta away from the boundary, which is at xi equal to 0. Okay, and so if I say that something is small over here, I better be careful about what smallness means. That it should be such that it is of the order or less than this cutoff over here. And with these provisos, I can say that this is a new solution of my model, which basically changes the boundary of ADS2. All right. So this is one class of solutions, which are those which change the boundary. Now let me look at a large class of solutions which don't change the boundary. I mean, and this is where somehow it took quite a while to understand this, because if you have a geometry with a boundary, you actually cannot fix the conformal gauge. If you allow for diffeomorphisms on the boundary, then the conformal gauge cannot be fixed. So this easy way of putting conformal gauge and solving equations is not available. So we have to use another gauge. This is this well-known Graham-Pfefferman type of discussion. So these fall-off conditions for my metric are these. And note this is order 1, it is not 0, like in the conformal gauge. And now I ask myself, what are the diffeomorphisms that preserve these conditions? So there is a calculation you do, but then modular gauge transformation. So you have to fix the gauge, and this is the so-called Graham-Pfefferman gauge. And if you do that, you can solve for these Killing vectors, and these are the solutions actually. Okay, so it's very, very nice, very beautiful. This even I can do actually, but the next step I couldn't have done. And this was done by Pranjal actually, that you can actually generate the full finite solutions, essentially by appealing to ADS tree, a slice of ADS tree, etc. All right, so this is some algebra over here.
But these new solutions, are they all diffeomorphisms of the original ADS?
Yes, I'm coming to that. That's yeah, here it is. That's right. So you start with ADS2. So again, you have an orbit. There's a point on the orbit which is ADS2, and you make this large diffeomorphism, and you arrive at a new solution. These new solutions have the same boundary conditions. And this is the metric actually. See? And the Schwarzian naturally occurs over here. So you have a whole class of solutions actually which don't change the boundary, which are parameterized by this function f of tau. And yeah.
So these are exact 0.
Yes. So you can also ask, how does the boundary change when I change there? How does the cutoff change? Now what is the cutoff in the new geometry? Huh? So that also can be calculated actually, because if zeta twiddle is equal to delta, then I can make a transformation, and it is given by this little wiggly curve around the straight line when delta is small. Okay. So in summary, the full solution that we think is important for the SYK model in the dual theory is given by these formulas. So you write it as e to the 2 phi times this new metric over here, and this metric is given by this formula, and phi is given by this formula.
SL2R is the part of this that does not wiggle the boundary?
SL2R doesn't do anything. Yeah, because it's an isometry of ADS2, right? Is 0 under that, right? Okay. So now, now that you have we have motivated our theory from a symmetry principle, and we now calculated the classical solution.
So
Now,
just to summarize,
sure.
I understand. You're saying
Yeah.
in the bulk, if you didn't have a boundary condition, you didn't worry about the boundary, then all solutions of this action are just diffeomorphisms of ADS2, And you might have thought that those would be pure gauge. Most of them would be pure gauge. But you say that when you put a boundary, you should, only those solutions are pure gauge that don't change them.
Yes. But there is a solution, important solution, that actually changes the boundary, which is important. That is this one. This one. You see the solution, the full solution has two parts, this one and this one, right? Your comment applies to this one. So this is just the orbit of ADS2 by a diffeomorphism.
Right.
Right? But there is something else. And that corresponds to the, in the SYK model also we had to resolve the equations actually to break the symmetry, right?
Right.
It corresponds to something like that.
Right. So you're saying that we should not think of diffeomorphisms that do not change, that change the boundary as pure gauge, that don't die out at the boundary as pure gauge.
Yeah. No.
And that's what's really.
Yeah.
And you're explicitly seeing an action because you've got a finite number.
Right.
And this action will go to 0 as delta goes to 0?
No.
No.
We'll see.
Okay.
It has to do with this phi. Yeah. Yeah.
Is that these guys, in the absence of this non-normalizable information,
In the absence of this one,
this delta G,
give right to zero action.
this guy would have been zero, exact zero.
Oh, man, I missed that.
Yeah.
So, however, in the presence of such a phi, we are not.
Ah, I missed that.
Yeah.
There would have been 0 modes even with the boundary?
Yes. Yeah.
So that's the difference from Brownhill. In Brownhill, it's actually all these Brownhill deformations, they're all normalizable, but they make it difference to the boundary field.
Right.
They give rise to stress tensions. Here, in the absence of this delta G deformation, the absence of this normalizability, they are genuinely, even though they are large deformations, they don't show.
And this delta G was just one of the SL2R worth of modes.
That's right. Yeah. So it's actually a non-normalizable.
No, not SL2R worth, but outside of SL2R. The delta G, yeah, 6 parameters, 3 were SL2R. It's the other 3 which are important.
So there's a trivial SL2R, and there's a non-trivial SL2R.
I missed this. What was the non-trivial? Sorry to explain. So what was the
Yeah. I'll show you. So here, let's go back to this one, no? This one. So if A, B, C, D are real, then this is the SL2R, and this you don't pure gauge, not important, pure isometry. But these are complex parameters actually.
Oh, this complex parameter doesn't make the solution complex?
No.
So there's another choice. Okay, with pure
You might have
imaginary.
written that solution up.
Yeah, I think you
in terms of the log solution for phi. Oh, you don't know that? There. Yeah. So this
Because it's
here,
GG bar.
because of GG bar, it's real.
Right. The solution is real always actually.
Okay,
Yeah.
interesting.
So this is mod G prime square.
Okay, so there are solutions of this model that are not just ADS2.
Yes.
Even
That.
up to diffeomorphism.
Yeah. This is the
I see.
point. Yes.
Yes.
Right. Okay. So where was I? So now you compute the action. I will be very fast. You basically compute the difference of the action. Okay. One on the full solution minus the one in which the f is set equal to tau, and you find basically that there is no contribution to the action. When you change from one along the orbit, there is no contribution to the action. But the boundary action changes, and it changes exactly by what you expect. It changes by the Schwarzian with this delta G upon B square outside. The delta G is small, just like 1 upon J was small in SYK. And B square is small, so that's like 1 upon N. So then the path integral of this two-dimensional quantum gravity from our perspective basically becomes this integral, and the correspondence with the SYK model matching of parameters is, as I said, delta G is small, it's of the order of 1 upon J. You make that identification, and B square is also small, so that because that's Newton's coupling, and so it's like 1 upon N. Now, one important thing I said before over the SYK model was that the it had a constant specific heat, like the free energy went proportional to the temperature. And this is an important point. This is important. This model produces that also. So that's good. So it matches with the SYK model, this type of thermodynamic, basic point of the thermodynamics. Now, of course, this is nice.
It doesn't have the ground state degeneracy, does it? The SYK model also has the ground state.
Yes, this the entropy at
Yeah,
zero temperature. It is there, but it's sort of cutoff dependent. There are a lot of cutoff dependent things, and we haven't been able to completely resolve this problem. Yes, because this is cutoff delta. The cutoff, this is the cutoff independent part.
Right.
But this we haven't been able to.
But generally speaking, even in the SYK model, that the zero temperature entropy has non-universal parts. It has one part which is just counts the dimension of the TIFR diameter. So that just
E to the n upon 2n, that's right.
But the other things, they depend on, for example, it depends on the this Q, how many fermions, interacting fermions are there in chemistry, and S.
So this part is not clear actually, but those are finite numbers, Gautam. Actually, see here, there's a cutoff dependence, and we don't know how to renormalize this theory
so
too.
But I'm
Yeah.
saying that even in the SYK model,
Yes.
isn't that right, Pranjal? Even in the SYK model, the zero temperature entropy has non-universal terms. Besides the first one, in log, which just counts the number of fermions.
I suppose what I was asking was that in your calculation there's a classical piece and a quantum piece. You get the quantum piece by doing this integral over the f's. But what about the classical piece? Just what is the free energy of your background?
No, so this has not been done because we are doing the differences.
Right.
So it would be this fellow. there.
Right, exactly.
Yeah.
Exactly. That's the thing that we normally compute
Yeah.
for black hole.
No, absolutely,
Right.
absolutely. So this is the difference fellow actually.
Yeah.
Yeah, yeah.
But since you have nice counter terms and so on, can you compute that as well?
I suppose so actually, but it has not been done. At least I have not looked at it. But for the ADS2 metric,
Yeah, in the thermodynamics, not with the,
So what-
the black hole, it is to black hole.
but what he's asking, does it match with the finite entropy at zero temperature? That is the question.
No, that it does not match with the SYK answer because we have some log terms that we could not resolve.
Log of what?
Log of the cutoff.
Cutoff.
In the finite calculation,
Yes.
there's a log. And then, so this is presumably a matter of finding the right counter terms on the boundary? Or not? Or logs are usually not.
Because
Logs are
we introduce counter terms actually to make many things finite,
Yes.
the correct counter terms, but not this one couldn't go away.
We could not find it.
Yeah.
Okay, interesting.
All right. Okay. So now, well, I mean, there are these issues about the tower of states, which I mentioned. These can be also incorporated in the in this theory as additional scalar fields, massive scalar fields. And the important point is that you know the coupling of these scalar fields with the so-called boundary graviton modes, and we are at the moment involved in trying to understand how to do the chaos calculation from the bulk rather than just ASYK type of thing. So this is what we are doing now
In Lorentzian or Euclidean?
in Euclidean. Yeah. But then, of course, you have to do an appropriate continuation.
Well, maybe we just directly do the Lorentzian space. That's a gravity is so easy to do in Lorentzian. In ADS we get this chaos exponent more naturally in Lorentzian space than we do.
That is true. That is
Check
true.
this out.
Yeah, absolutely right. I don't know how else to do it either. How else to do it either, I don't know. Unless you have this facility to throw in something and it collides with something.
Right.
That's a very Lorentzian.
Yeah.
Yeah, good. So let me just end with some further problems. I think Sandeep Trivedi was there in my talk in Greece, and he made a remark which I thought was rather important, that we have been working with smooth geometries. If you want to see the origin of these other states, perhaps we have to understand geometries which are singular, in which, for example, this holomorphic functions I talked about can admit zeros and poles. It's a thought, haven't done much about it. The other thing which might be well worth noting is that Polyakov's model, which I wrote down, of 2D gravity, essentially has a exact formulation in terms of SL2R current algebra. And so the action can be written in terms of the Sugawara construction, and there are, just the way we do West-Zumino in theory, but for SL2R with some additional constraints. So maybe if we can solve this type of gravity theory exactly also and understand its Hilbert space, beyond the semi-classical approximation around single geometries, it can be useful, I think. And I think let me end by saying that the really key problem is to solve the problem at finite n, because that is the unitary problem. Moment you take n goes to infinity, unitarity is out of the window, because the way the spectrum is coarse-grained. So if we can only solve some of these type of models exactly in some way, then learn to take the large n limit, we may be able to understand how this coarse graining actually gets rid of unitarity and all these important questions actually. So anyway, thank you. Sorry for all the problems with my computer setup and all that. Because I didn't explain the method of co-adjoint orbits for Virasoro.
Questions from ICTS?
Oh, there are people there? I thought there was some faculty meeting now.
I can see Loga there.
It's okay.
Sorry, I didn't have any questions.
Questions from Mumbai?
So I just going back to a question at the beginning of the talk. Stanford and Witten have computed the exact partition function from this.
Yes. Yes. They just did the integral.
Just the integral. Now, if it is true that this Schwarzian action corresponds to some part of the Hilbert space, there's a check, right? There's a question is that partition function, is it the partition function of any Hilbert space? Meaning, is it sum over an e to the power minus, integer, where an's are integers, an times e to the power minus beta e? I strongly suspect the answer to that question is no.
It might just be, Shiraz, that this may be true in the dual representation. I mean, in the dual representation, you have a field which is a function of time and space, and you may be able to.
Actually, I'm not even looking at the representation now. I'm just looking at the answer. So we've got a partition function. Now you can ask, is this a partition function over any Hilbert space? What was the answer for the partition function? Was it effectively like something going like t or some power of t, some very simple thing?
Yeah, exponential of 1 upon g to some power times. Yeah, okay.
I think we'd very quickly be able to show that cannot. Maybe they can show it from that cannot come out of summing over integers.
They have a remark in the paper. They have some guarded statement about in this particular the free energy of this particular sector, it does not have quantum mechanical interpretation, but they made some guarded statement about the whole thing because they were only talking about that. I don't remember actually.
It's very, if you take an arbitrary function of temperature, and if you claim that's an exact result, then it's very strong. It's a question of, can you write it as a sum over integers times e to the power minus beta, beta. Now, if the free energy has some large number outside, I mean maybe, but here the free energy will have one outside, and it sounds basically very unlikely. They probably checked that.
I don't know. I don't know the
But
answer to this.
I think that unless a miracle happens, the answer will probably be no. Assuming that's the case, that I think tells us that you cannot associate a Hilbert space with this thing, because at least not in a unitary.
Let's think about it this way, that suppose I start with the original partition function,
Correct.
and original partition function can be written in terms of sum over exponential of eigenvalues, whatever.
No doubt.
No doubt. Now we are restricting ourselves to some part of the spectrum.
But this is, you're restricting yourself to a part of the path integral. It's not clear to me you're restricting yourself to some part of the spectrum. You've done Euclidean, this is a purely Euclidean calculation.
Yes.
You've got a saddle point and you're isolating on a particular fluctuation around this.
So partition function is a Euclidean thing. No?
Exactly. I want to know whether this particular restriction of the path integral corresponds
To some yes, some part of the spectrum.
It seems to me there's an algebraic check of that.
Yes.
Because these guys can
Yes.
do the answer exactly.
Yes.
Now you can just ask, if it were the partition function over some spectrum, find the spectrum.
So one can take the inverse Laplace transform of this answer
Exactly.
and see whether you get the.
What you get is a continuum. A continuum with weights which are infinitesimal, rather than discrete weights on. Do you know what I mean?
I know what you mean, but
Yeah. This is the kind of
yeah.
Witten's original proposal for 3D gravity failed on this count. Do you know what I mean? He had a proposal for an exact partition function.
Yes.
It failed on similar.
That it is not given
But
by.
his original proposal satisfied this, but then a modification that he might have suggested, which is he had this paper with Maloney, which is compute just the orbits over SL2R. You could do that exactly.
Yes.
And then they could show that the answer just was not a sum over integers.
I see.
I suspect it would be similar.
So this is just a matter of looking at the inverse Laplace transform.
Laplace transform.
And then you get rho of E basically.
Exactly.
And you see whether it is sum over delta functions.
Sum over delta. Exactly.
That's what.
That's what I'm saying.
Yeah.
And
So that can be checked.
That can be checked. It would be surprised me if Witten hasn't checked.
Yeah. Yeah. Okay. I didn't read that paper very carefully, but perhaps there is some remark there.
What will be wrong with the spectrum is continuous?
Spectrum can be
Continuous,
but
then.
the number of states has to be infinite. If the spectrum is continuous and the total number of states is finite, then it can't be all the weights are infinite. It's not even really continuous. It's the fact that wherever it clicks, the coefficient has to be infinite. Okay. Now that statement plus continuum means that the total number of states is infinite.
Yeah, I suspect that this. Suppose your n was finite, then I don't know how to derive this Schwarzian or anything. You see, n finite. So if n is large and all that, and you are massaging this theory and taking n upon beta j to be arbitrary after that, I have a feeling that the spectrum is already it's not discrete, I think.
Right. Right. So I think that you would conclude from that you cannot associate a sector of the Hilbert space with this. I don't know. You guys know this much better than me.
Unless. Yeah, but the spectrum can be a continuum also, no, Shiraz, in large n limit. I mean, the discrete part I give you, but it can be a continuum, right?
Right. If you've got a Hilbert space with a finite number of degrees, let's say n is some finite. So it's finite dimensional Hilbert space.
Yes.
Below any energy.
Yes.
So it just has to be a sum of individual delta functions.
Yes.
If you've got a finite number of states and the sum of delta functions, you cannot have a continuum.
But that will happen at finite n.
But these guys tend to do it exactly.
Yeah, but you see what they have done. They have some Schwarzian theory in which there is a coefficient, and that coefficient is n upon beta j.
Right.
That was derived in the large n limit by somebody.
Okay.
Okay. Now they want to actually talk about large fluctuations of this reparameter. Parameter. So they are saying, let us do the calculation exactly.
Right.
But you are computing an integral exactly which you arrived at in a certain approximation from the full theory.
Right. So
This is
maybe this thing gets correct. The effective action gets corrections and fine.
Yeah.
I don't think theirs is an exact n.
No, it is not.
Yeah.
It is not. That's
It's an exact calculation given the action, but you're saying that the
Yes.
starting point to get.
yes, yes. So I agree with you that the spectrum will be a continuum.
Maybe there's some way of fixing this up so that.
I don't know really actually. Yeah, I doubt it. Okay. Thank you.
Other questions?